Good morning, students. In the yesterday's class, we were discussing about the basic functionality of oscillators, and we are primarily focusing on the sinusoidal oscillators. The reason is, in most of the analog applications, it is the sinusoidal oscillators which are going to be useful because those oscillators have a continuously varying waveform. There are many other types of oscillators, especially in the digital domain. All digital circuits are working by means of a signal called clock, and for clock generation also there are oscillators. They are actually digital oscillators. But here in our course, we are focusing more on analog type. So, yesterday we were discussing that in this particular expression, if A beta or A into B becomes 1, then 1 minus 1 becomes 0 and AF will be infinity. That means the gain with the feedback will be infinity. And if A beta has to become 1, then there must be phase shift introduced even by the feedback network. Otherwise, A is having a negative sign, and if beta is also having a negative sign, minus into minus becomes plus. So, if the amplifier is producing 180 degree phase shift, the feedback network also should produce 180 degree phase shift. Then, if this condition is met, A beta equals 1 condition is met, then the amplifier itself will become an oscillator with the positive feedback without any external input at all. So, the question now is, if the amplifier becomes an oscillator and as soon as we switch on, let us say the circuit produces an output of a required frequency, then how come the initial signal is coming into picture here? As soon as the amplifier switches on, what is the initial signal by means of which the same signal gets amplified? So, for that, the answer will be explored in today's class. Let us go to the next slide where I will tell you how come the initial signal is present in the amplifier itself. So, the starting signal is the infinitesimal noise voltage, which is always present and contains all the frequencies due to the random movement of the free electrons. As soon as we switch on, the amplifier circuit will not immediately come to the quiescent point. It will take a finite time for the transistor to come to the quiescent point. That means initially it will be off only. To turn on half, it takes a finite time. Now, when this transistor takes that finite time, there are always movement of electrons within every material as such. Now, inside the transistor, as it is a combination of many junctions as such. In case of BJT, it is collected to be a base and base to emitter junctions are there. Even in the case of JFET, between the gate and the channel, there is junction. Now, wherever there is this dissimilar material, one N type and one P type, wherever there is a dissimilar material, whenever electrons start moving among dissimilar materials, gradually there will be noise. And the noise in the normal case will be negligible. But in this case, as the noise itself is getting amplified and fed back and amplified and fed back, gradually after a few microseconds or after a few milliseconds, it is not even seconds, because within that time the transistor will come into active region. In between, there is this noise which is due to the random movement of electrons, and this infinitesimal noise itself gets amplified. So, the starting signal is the infinitesimal noise voltage, which is always present. In the normal applications, we can ignore it many times. For example, when you and me are now communicating through this classroom, maybe online class, still we will have noise around us. Around me also there will be noises, around you also there will be noises. But in most of the cases, these noises can be ignored because these noises will be of lesser amplitude. But what happens in an amplifier? In an amplifier, the noise gets amplified, right? And the same noise is fed back through the feedback circuit. It gets further amplified and it goes on like that. Now later on you may ask, if it keeps on going amplified, now later on it may become distorted also. Now to prevent the distortion, we have these measures here now. Otherwise you may think it will keep on infinitely getting amplified and sine wave may become a square wave, only transistor will be switching on and switching off between cutoff and saturation if it is BJT. You may think that way. No, it does not happen because we have some other mechanism to prevent the transistor going into cutoff and saturation. That I will tell you later on. So the starting signal is the infinitesimal noise voltage, which is always present and contains all the frequencies. When it contains all the frequencies from 0 to infinity, how do we pick up a particular frequency which we want? Again, that is a question. For that we have an answer. The answer is the feedback circuit. The feedback circuit is a frequency selective circuit. In our earlier cases, the feedback circuit was only taking a small portion of the output voltage and it was feeding back to the input in the case of the negative feedback. But now we are discussing about the positive feedback. In the case of the positive feedback circuit, the feedback circuit itself is a frequency selective circuit. On the other hand, we can also call it as a tuning circuit. We will see that later on. So, the noise voltage which is always present contains all the frequencies due to the random movement of the free electrons. The amplified noise drives the resonant feedback circuit. You can see I have marked that resonant with a different color purposefully. The feedback circuit is not a normal circuit now. It is a resonant circuit, means it will have resonance. You have already studied this resonance in the course called network analysis. When XL equals XC, when there is an inductance and a capacitance, whenever XL equals XC, we call it as resonance. There can be series resonance, there can be parallel resonance. That means when the reactance is minimum, at that time the passing of the signal through that circuit will be maximum, and then we say that particular circuit is a frequency selective circuit. That means at a particular frequency only it offers minimum resonance, minimum reactance. And why do we call it as resonance? Because what is basically resonance? Resonance means when you have, let us say, one string is being moving in a guitar or a sitar or a veena, you can also see a minute movement with the neighboring strings also. Even though the neighboring string is not moved, still the effect of the other string which is moving will cause some movement in the neighboring string also. That is because that vibration is nothing but vibration of the air column in between. The air molecules are going to vibrate in between. Now, if something else induces vibrations with some other circuit element, we can call it as resonance. So, this feedback circuit is a resonant circuit. In the sense, it is a frequency selective circuit, and hence oscillations build up at the desired frequency. We can get the desired frequency because it is only the desired frequency which is passed through the feedback circuit. Even though the amplifier is containing all types of noise within, they are all infinitesimal. Feedback circuit is going to pass only a particular frequency value through it because it is frequency selective. So that particular frequency goes back to the input and gets amplified, and that is how the oscillator starts oscillating only at a particular frequency. Because a particular frequency which was a noise earlier is being amplified by the circuit. So that is the idea of oscillations. Now, how do we prevent the oscillator to saturate, or how do we prevent the oscillator not to distort the output signal? We will see that now. You are seeing now three waveforms here. the waveform at the right side is dying out gradually, and waveform at the middle is gradually building up, but the waveform at the rightmost is stable. Now this is called sustained oscillation. Now let us say oscillation starts in the beginning and later on oscillation does not go along. Now we say the oscillations have died out. Let us say you move a string in the veena or a guitar or a sitar. Now only when you move it will produce a sound, later on sound will die out because the vibration of the string will stop. Now in such a case oscillation does not continue. That is called damped oscillation. The oscillation which you are seeing here at the left side is called damped oscillation. Means oscillation is there only in the beginning, then it will die out. Now the oscillation which you see in the middle is the oscillation which is infinitesimal and gradually it increases because of the amplification. Now you may think amplification keeps on increasing, so it may keep on increasing further. It may go to 0 till VCC and gradually it will keep on becoming that way, and there will be distortion in the sine wave. That you may think now, but we have a mechanism in the circuit there where we have a particular stability analysis where we make the circuit to oscillate only in this particular amplitude. How it happens later on we will see. So the signal which you see at the right side is called sustained oscillation. Means after the circuit reaches a particular value of or amplitude of these oscillations, later on there will not be any further increase. Again that depends on that particular factor A beta. Even though A beta is 1, oscillation will not increase further, and that A beta itself is causing that way. Let us see that later on anyhow. So you can see that at the left side there is a damped oscillation, at the middle there is a produced oscillation which is in the increasing amplitude, but at the rightmost side you will see that it is called as a sustained oscillation. Means the oscillator circuit will keep on producing the same amplitude, the same frequency continuously without any further distortion. Now as soon as we switch on the oscillator circuit, within a few microseconds or milliseconds, the circuit will stabilize itself, because it is basically the movement of electrons only there, right? And in general we assume the speed of electricity as the speed of light. Even though we have not fully measured the speed of electricity anywhere and it is not of much use for us also, still we generally assume or presume that speed of electricity and speed of light are one and the same. The moment you switch on, the moment the electrical appliance will start working. Now from the switch to the electrical appliance there is a wiring, and we generally presume that the moment you switch on, instantaneously electrons will move in the copper conductor so as to power up the electrical appliance. That means it is assumed that the speed of electricity is same as the speed of light. That is why I told the oscillator circuit will stabilize within few microseconds or few milliseconds. We will not be able to find out the difference of delay there also. That is why we say as soon as you switch on the oscillator circuit, it will start working. Now the first case where there is damped oscillation, that is because A beta is less than 1. When the gain of the amplifier and the feedback factor, the product of them is less than 1, oscillations will die out, because it will not be further amplified, because it is less than unity. The second case, when A beta is greater than 1, then what happens? When A beta is greater than 1, oscillations will keep on increasing their amplitude, because the loop gain is more than unity. Now if the loop gain is equal to unity, if we maintain A beta is equal to 1, then it will keep on producing sustained oscillations. That is why I told you the A beta itself is the decisive factor for sustained oscillations. And when we design the circuit, we have to take care in such a way that amplifier gain and the feedback factor, their product will be always equal to unity. Now there is something called Barkhausen criterion for the oscillations now. Whatever has been discussed till now, that is put as a summary. That is called as Barkhausen criterion, which simply says magnitude of loop gain should be unity at a phase angle of 180 degree. That's all. Magnitude of loop gain should be unity, means A beta should be equal to 1. But at a phase angle of 180 degree, means what? That feedback circuit also should produce 180 degree phase shift, which was not there in our previous case of negative feedback. Here in our earlier negative feedback circuits, the formula for AF was A by 1 plus A beta. Now here the formula is AF equals A by 1 minus A beta. That means at a phase angle of 180 degree, even the feedback circuit produces 180 degree phase shift. So this is actually the Barkhausen criterion, which means if the loop gain is unity and if it is minus 1, that means at a phase angle of 180 degree, then the circuit is definitely going to work like an oscillator. This is the necessary and sufficient condition for oscillation. I will repeat, the necessary and sufficient condition for oscillation is called as Barkhausen criterion, where A beta must be 1 and the feedback circuit must produce 180 degree phase shift. That is the idea here. Now let us discuss more about the feedback circuit itself. I had shown you this circuit earlier also. I am going to show you once again. We call it as bypass circuit or low pass circuit or as a lag circuit. You can see this circuit, RC circuit. Now capacitor will charge through R, again capacitor will discharge through R if there is no load connected here. So the output that is taken across the capacitor will always be an integrated version of the sine wave. Of course, you know that the integral of sine is cos only. So in this particular case, when the input is sine wave, output signal will not be having any distortion in the waveform, or it will not have any waveform deformation, I should say. It is not distortion because it is an integration of the input signal. The wave shape is not going to change because sine and cos are going to have the same wave shape except for the angular differences. So now this is called as a bypass circuit. Why is it called as a bypass circuit? Because if at all there is a high frequency, capacitor will offer much lesser reactance and the signal will go to ground. We had utilized such capacitor in our common emitter amplifier at the emitter. For the same reason, this circuit is called as bypass circuit. It is also called as low pass circuit. Why? If there are low frequencies at the input, for the low frequency, capacitance will not offer lesser reactance. You know that Xc equals 1 over 2 pi Fc. When F is very high, then the capacitance is going to offer much lesser reactance and the signal goes to ground and output will not be having any value at that time. That is why it is called as a low pass circuit. Low frequency gets passed to the output. High frequency will not be available at the output. It is also called as a lag circuit because there will be a angular lagging between the output and the input. And regarding this leading and lagging, I hope it has already been taught to you again in the course called network analysis. We have so many courses which are relevant to each other or connected to each other. So the reason for lag circuit is already known to you. Now when we apply the mathematical analysis for this circuit, we have this V out by V in is equal to Xc divided by square root of R square per X3 square. You are already familiar with this particular formula. We are taking the output across capacitance. So it is nothing but a reactance divided network, I can say. There is a resistance, there is a reactance. We cannot directly say it is a resistor divider network. We cannot directly say a reactance divider network also. I feel we can say it as impedance divider network because there is resistance as well as reactance. So V out by V in, the ratio is Xc divided by R square plus Xc square, and the angle is nothing but tan inverse of R by Xc. The angle between output and input is minus arctan. Arctan is nothing but tan inverse. Tan inverse of R by Xc. You have already become familiar with this particular expression also. Now this is called bypass circuit or lag circuit or low pass circuit. Conversely, we have another circuit called coupling circuit. Now this is a coupling circuit. Why? We had used a capacitor in our amplifier at the input as well as the output for AC coupling. Now if capacitor is in series and resistance is in parallel, then we call it as coupling circuit because AC gets coupled through the capacitor. Now also capacitor is going to charge through R only, discharge through R only, but only the connection is reverse way. Means if there is no particular load, then the capacitor is just discharging through R only, or it is getting charged also through R only. So that RC time constant or tau remains the same here. But the nature of functionality of the circuit will change. That is because now it is like a high pass circuit. High pass circuit in the sense, if there is high frequency, X is 1 over 2 pi Fc. So for all high frequencies, capacitor will offer very less reactance and all the high frequencies are available at the output. But for low frequencies, the capacitor will offer higher reactance. So low frequencies will be partially blocked by the capacitance. High frequency will be passed through the capacitance. That's why it is called high pass circuit. And it is called as lead circuit because in this case, the angle will be leading instead of lagging. That is again because of our mathematical analysis. So the ratio here is V out by V in is equal to R divided by square root of R square plus X square because we are taking the output across the R now. Again it is a impedance divider network, I should say. But here you can see the angle is not negative, it is positive. So phi is tan inverse of Xc by R because the capacitor is now in series. Now using these circuits, we can introduce phase shift also. We can make this circuit frequency selective also. Of course, as far as R and C are concerned, we will not be making them frequency selective, but ultimately the circuit will become frequency selective that way. But we can use these circuits for introducing phase shift, and by means of which, if we make the Barkhausen criteria to meet, then automatically circuit will become oscillator. We have to make A beta equals 1 and we have to introduce 180 degree phase shift in the feedback network. If these two conditions are met, then automatically the amplifier will become oscillator. So that is possible. So that way we are going to use this bypass circuit or the coupling circuit as feedback circuits in our oscillators. These are examples of phase shifting circuits from 0 degree till 90 degree depending on the frequency. Now, this lead circuit or lag circuit, it can introduce maximum 90 degree phase shift. As you already know by the application of this particular formula, it can produce maximum 90 degree phase shift, right from 0 degree phase shift. Now, whether we have to use exactly 90 degree, then in that case, we will have to connect two circuits. Because we want, in the feedback circuit, we want 180 degree, which means if we connect two such circuits, 90 plus 90 will become 180. But 90 is the maximum possible angle. Now, why should we always have that risk of taking only two circuits where it will produce 90-degree maximum? Instead, anyhow, these circuits are going to produce from 0 till 90. What we can do is, instead of 2, we can connect 3, where each one will produce 60 degree. If each one produces 60 degree, it is 60 plus 60 plus 60 is 180. So that is a good combination. Now you may ask, why only 3, sir? Why not 4? Yeah, 4 is also possible. Let us say we connect 4 such circuits. Each one is going to produce 45 degree. Then 45 plus 45 plus 45 plus 45. That is also possible. So we do not use only 2 such circuits in the feedback network. The reason is maximum angle itself is 90 degree. Now we can go between 0 to 90. That means either we can go for 3 or we can go for 4. We can go for still more circuits also. But here the point is, why should we unnecessarily connect more number of components in the feedback circuit? If the purpose is served by 3, we need not go for 4. Of course, we cannot take only 2 because, as I have been telling you, 90 degrees is the maximum angle. Why do we take risk there? Instead, let us go for a compromise in between 0 and 90. It is very logical to use 3 such circuits where each will produce 60 degree and 60 into 3 becomes 180 degree. Why should we go for one more circuit as 4 circuits where each will produce 45 degree but the number of components will increase? Why? Unnecessarily space also is going to be wasted, cost also is going to be increased. That is why in general now, in the first oscillator that we are going to discuss, we will have 3 such circuits where each one will produce 60 degree phase shift. If you have any questions in between, you can always put in the chat box. I will keep watching the chat box. So let us discuss the first oscillator called phase shift oscillator. You can see an amplifier here, then you have a CR, CR, CR. There's a feedback network. Now, each CR is going to produce 60 degree. Together, totally it is going to produce 180 degree. That is the idea here. Now, here we have connected the lead circuit. Now, you may ask, can we connect the lag circuit also? Yes, you can. We can connect the lag circuit also. Okay. But practically we will have some problems later on. That I will tell you later on. Right now, when we are dealing with an ideal amplifier, for an ideal amplifier, we can connect a CR also, we can connect an RC also. Ultimately, all 3 are going to produce together 180 degree. Whether it is a leading circuit or a lagging circuit, it does not matter in our case. Okay. But we prefer this CR only. The reason I am going to tell you later on. Because we are not dealing with ideal amplifiers, we are going to deal with practical amplifiers. Let me admit the student. So let us proceed. Here, beta is supposed to be 1 by 29 and hence A is supposed to be greater than or equal to 29. Now, why beta is supposed to be 1 by 29? That analysis is beyond the scope of our syllabus. Because we will have to perform a frequency domain analysis for this complete circuitry, and it is a very lengthy and elaborate procedure to perform frequency domain analysis. You have already become familiar with the frequency domain analysis for the passive circuits. But now for the active circuit, here we have an active circuit amplifier and we have a passive circuit in the feedback. We will have to apply frequency domain analysis for the complete circuit now. That we have not kept in the syllabus of undergraduate program. The reason is, it is unnecessary to go through all those elaborate and bigger steps now. It is going to take a longer time, but ultimately the result is the same. Scientists have already performed that frequency domain analysis many decades before, and the results are available with this. We need not derive those formulae once again. So when we discuss all these oscillators now, the proof of those formulae is not there in the curriculum. That is purposefully made because it is a wastage of time in going through elaborate mathematical procedures for performing frequency domain analysis. You will not find that proof in our textbooks also. Even the textbooks authors have purposefully avoided it. But if any of you are curious to know about why this 1 by 29 came into picture, then you can always go through Google. Google sure knows everything. So you can go through Google and you can find out. There are websites published by the scientists themselves where they have published all these results. So this beta equals 1 by 29 is the result of the frequency domain analysis for this particular circuit. Therefore, when we have A beta should be equal to unity, right? When A beta must be equal to unity, A must be either greater than or equal to 29. We will say equal to 29 when A beta has to be 1. But if A is greater than 29 also, it does not matter. Now you may say, if A becomes greater than 29, then A beta becomes greater than unity, right? If it becomes greater than unity, we will have a stability issues, right? But the stability issue can be later on compensated by means of some compensating network. I am going to discuss the practical limitations later on. So right now, let us think beta has to be 1 over 29, hence A has to be greater than or equal to 29. Now each RC stage provides a phase shift of 60 degree at a specific frequency. At a specific frequency. Why? Now R and C has become a frequency selective network only because of the leading or lagging property in the angle. So the phase shift of 60 degree is going to happen at a specific frequency, right? Range is from 0 to 90 degree. Please remember, the range of angular difference is between 0 to 90 degree. But now, when this is going to become totally 180, when this is 60, this is 60, this is 60. When this is going to become 60, it is actually from 0 to 90. At one particular frequency, it is going to become 60. Because it is dependent on XC and R both, right? So you know phi equals tan inverse of XCR. So in that way, when the angle is related, the total network is to produce 180 degree phase shift only at a specific frequency, not at all the frequencies. Imagine. Now let us say we are designing an oscillator for 10 kilohertz. Now only at 10 kilohertz this RC will produce 60 degree. Imagine that way. So 60 plus 60 plus 60 becomes 180 degree only at 10 kilohertz. But at 11 kilohertz, this will not be 60 degree. Or at 9 kilohertz, this will not be 60 degree. It may be 59 degree or it may be 61 degree. If it is 59 degree, the net phase shift will not be 180 degree. It will be lesser. If it is 61 degree, again, the net phase shift will be more than 180 degree. Then the circuit will not become an oscillator. Circuit will not work like an oscillator. That is the beauty here. Which means, even though we have chosen RC, even though it is not frequency selective, we made it frequency selective by combining 3 such circuits. And we know that only when the feedback network produces 180 degree phase shift, only then there will be oscillations as per the Barkhausen criterion. Now, if that has to happen, this has to produce 60 degree only, but it will produce 60 degree based on the value of the capacitance, based on the reactance of the capacitance, and that will happen only at a particular frequency. So each RC stage provides a phase shift of 60 degree at a specific frequency, not at all frequencies. At different frequencies, the phase shift will be different. Now, provided the loading effect is taken care of. What is the meaning of loading effect? Here we assume it is an ideal amplifier. If it is an ideal amplifier, it will not take energy from the feedback network. That is our idea. That means input impedance should be much larger such that there will not be any loading effect of this R to the input impedance of the amplifier. That is the idea. See, we have this R in parallel here. Now this R, last R, or from the left side that particular R, that is in parallel with the input impedance of the amplifier. You will have to visualize a Zi here. You will have to visualize, let me change the color. You will have to visualize one resistance here, and this is now Zi, or the input impedance of the amplifier. Now, when this R is in parallel with Zi, naturally what will happen? The phase shift will not be 180 degree. See, this is C and R, this is C and R. Now, this is C and R parallel with Zi. So, naturally, the leftmost circuit will not produce 60 degree phase shift because the value of R has now changed. Now, in this case, we have assumed that the amplifier is ideal. When the amplifier is ideal, Zi is very high. If Zi is very high, Zi in parallel with R will not have much effect, because when our two resistances are in parallel, whichever is the least resistance, value will be having lesser than the least resistance. Whenever these two resistances are in parallel, if one of the resistances is very high, then the effective parallel resistance will be equivalent to the least resistance. Now, if Zi is very high, ideally, then Zi can be completely ignored as far as the parallel combination is concerned. Then this RC, 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 each one will produce 60 degree and the circuit will work like an oscillator. That is the meaning of this loading effect, provided the loading effect is taken care of. Later on, we will see how the loading effect is taken care of. Now, the formula for this phase shift oscillator is 1 over 2 pi RC into root 6. Now, as I have told you, the derivation of this particular formula is beyond our syllabus. We will not discuss it. We will only use this formula for our purpose. That's all. Both in the theory and both in the lab, we are going to use this formula for our purpose. We are not going to derive this formula. But remember, F equals 1 over 2 pi RC root 6, and that root 6 is coming because of the mathematical computation of this circuit itself. Now, we already know that op-amp will have a very high input impedance and op-amp will have a very low output impedance. You already have studied the basics of the operational amplifier. So now, to the output of the amplifier, we will connect one CR, 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 and lastly we will connect it through one more resistance RI and with the feedback resistance RF. Why do we need this RF and RI? Because ideally, op-amp's voltage gain is infinity. Op-amp's input impedance is infinity. Output impedance is 0. Operational amplifier is almost ideal compared to the normal amplifier. Now, you can see whatever is this A is a normal amplifier, which we have been discussing. Common emitter and common base and common collector amplifiers we had discussed with BJT. Now, operational amplifier is not a single amplifier. It has got multiple stages within. You will be studying the internal circuit of operational amplifier in the coming semester in a course called linear integrated circuits. So, as of now, assume that operational amplifier is almost an ideal amplifier. So, its input impedance is infinity, output impedance is 0, and even the gain is infinity. Now we will have to reduce the gain of the op amp. That is why we use this feedback resistance and this input resistance. You already know that for an inverting amplifier, the gain is nothing but minus of Rf by Ri. You already studied that formula in basic electronics. Now, amplifier has to produce 180 degree phase shift and the feedback network will produce additional 180 degree phase shift, right? Now, if amplifier has to produce 180 degree phase shift, it has to be an inverting amplifier. So, op amp is used as an inverting amplifier and we can set the gain. In general, here this A into beta must be unity, right? So, in general, what we do is this Rf by Ri, we set it as 1 only. We set the op amp gain as unity itself. And then we use this RC network for producing 180 degree phase shift. Now, the op amp is going to produce 180 degree phase shift because of its inverting configuration, and this CR network is going to produce 180 degree phase shift. And RFI RI is used for setting the gain. That way, this is now an integrated circuit phase shift oscillator. Why is it called as integrated circuit phase shift oscillator? That is because operational amplifier itself is an integrated circuit. It is not a discrete circuit. Operational amplifier is available as a silicon chip packed with either ceramic or plastic package with pins outside so that we can solder the pins to our printed circuit board and we can handle this package through our own hands. Otherwise, the chip is really very small. The silicon chip is really very small. The chip needs to be handled carefully. That is why it is packed with the bigger pins at the outside with the sufficient distance between them. Typically, a distance between two pins is 2.54 mm. That's a standard. So, operational amplifier is basically an integrated circuit. Now, using an integrated circuit, we are constructing a phase shift oscillator. That way, this is a integrated circuit phase shift oscillator for which this formula is applicable. F equals 1 over 2 pi RC root 6 is applicable. Now, how can we design this operational amplifier's phase shift oscillator? Design is simple. Let us say you want to design an oscillator for 10 kilohertz. You know F equals 10 kilohertz. Formula is given 1 over 2 pi RC into root 6. Now, choose C of a particular value. Later you can compute R. Or choose R of a particular value. Later you can compute C. I am repeating. See, let us say we want to design an oscillator having a frequency of 10 kilohertz. Now, 10 kilohertz is here at F. 1 over 2 pi RC root 6. Now, R and C both are unknown. When R and C both are unknown, when we have two unknowns, we will have to assume a value for one of the unknowns. Let us say R we choose as 1 kilo ohms. When we choose R as 1 kilo ohms, you can substitute 1 kilo ohm here, you can substitute 10 kilohertz here, you can obtain the value of C. On the other hand, you can assume C also as 0.1 microfarad. If you assume C as 0.1 microfarad or 100 nanofarad, you can substitute the value of C, substitute the value of F, then you can obtain the value of R also. That way, whenever we have two unknowns, one of the unknowns must be assumed with the particular value and then the other unknown's value can be calculated. In that way, we are going to proceed for designing the oscillator. So, in the next class, we will see some designs of the oscillators. As today's time is already up, I am going to end the class now. See you in the next class. Take care and goodbye.